Hello everyone, welcome back to our channel. Let's discuss the next named reaction, that is Boekelheide reaction. Let's see the statement. By using this statement, we are observing that we will be converting 2-methylpyridine N oxide into the corresponding 2-hydroxymethylpyridine. This is very much helpful in the conversion of pyridine N oxides into its corresponding pyridines with the hydroxymethyl substitution. Let's see, we know that pyridine structure. This is the pyridine structure or not? At the second position, what we need? Hydroxymethyl. If you place CH3, that is methyl. But what I need? Hydroxymethyl. So I need to replace one of the hydrogen with OH group. That is hydroxymethyl at the second position. So this is our product. Okay. What will be the reactant? I need to take pyridine N oxide. Oxide means connected to what? Oxygen. Oxygen is having only one bond, but valency is 2. That's why O minus. Nitrogen valency is 3 only. Here we have 4 bonds or not? 1, 2, 3, 4 bonds. That's why we have positive charge. At second position, we should have the methyl group. So in this way, we need to convert the pyridine N oxide, 2 substituted pyridine N oxide into its corresponding hydroxymethyl derivative by using acetic anhydride or trifluoroacetic anhydride. Acetic anhydride structure is CH3, C double bond O, O, C double bond O, CH3. So trifluoroacetic anhydride means C double bond O, C. So all hydrogens are replaced with fluorine atoms. Okay. So let's see the mechanism. So the reactant is 2-methylpyridine N oxide. Here we have taken. So oxygen is having minus charge. Nucleophilic character is readily available. It is going to treated with your acetic anhydride or trifluoroacetic anhydride. So we can take any one of these two. So now see what is happening in this C double bond O. Carbon is electron deficient center or not? That's why O minus is donating its minus charge to this carbon. The pi bonding electrons forming a minus charge. Again it is creating its positive pi bonding character. Right? In order to maintain its valency, what is happening? These single bonding electrons are cleaving. These are moving towards the oxygen. Here the oxygen will take minus charge. See this. O minus C double bond O CF3. So we are coming up with what? Oxygen is forming a bond with carbon. See this. Oxygen is forming a bond with carbon. C double bond O CF3. C double bond O CF3. Okay. So for our convenience, I am writing the resonating structure of this one. See this. The pi bonds are arranged here. Here the pi bonds are arranged here. Okay. Now what is happening? At the second position we have CH3 group or not? That can be written in this form, CH2H. So from that hydrogen is removed in the form of H plus. The H plus is attaching the O minus and removing in the form of trifluoroacetic acid. So by removing the H plus, we are creating minus charge at the carbon or not? So the minus charge is forming a pi bond here. Thereby these pi bonding electrons move towards the nitrogen. So nitrogen is taking the minus charge or not? Already positive is there. The minus and plus will be neutralized or not? See this. The pi bond is converted into single bond. The positive charge is neutralized. Here the single bond that is converted into pi bond. So O C double bond O CF3. O C double bond O CF3. So here we are going for the breakage of nitrogen oxygen bond. See this, what is happening? In case of the pyridine, we need 3 alternative pi bonds or not? That's why what we are doing, we are sending these pi bonding electrons to this bond. That's why we have created pi bond here. Thereby electron deficiency is developed here. Positive charge is developed here. So here nitrogen valence is enhanced. That's why these bonding electrons forming a pi bond with this one. So these pi bonding electrons moving towards oxygen. Oxygen will take the minus charge. The minus and plus combined each other to form a CH2O bond. So CH2O C double bond O. At the final step, we need to do the hydrolysis phenomena. Thereby, OH will attach here, H will attach here, trifluoroacetic acid will be removed, and we will come up with CH2OH. So simply, by this reaction, what we are observing, in case of the pyridine N oxide, at the second position, we should have a carbon atom. That carbon atom should have at least one hydrogen. At least one hydrogen should be there. That hydrogen is simply replacing with OH. That you need to understand. Simply replacing with OH group. Clear? Let's see some of the applications. Here see the group. So pyridine N oxide. At the second position we have CH3 group. So one of the hydrogen will be replaced with OH. Very simply. Okay. So here hydrolysis is must. That we need to understand. By using the HCl we are doing the hydrolysis. Otherwise, if you will not do the hydrolysis phenomena, we will not come up with this final moiety. The final moiety will be the acyl derivative. Okay, it may be OC double bond OCF3 or OCH3. If you use acetic anhydride, this one will become CH3. This can also be written in this way. In case of acetic anhydride, we can write CH2OAC. Acetyl group, CH3C double bond O. Okay, let's see some more examples. Here it is the reactant, pyridine N oxide. At the second position, here see, here we have CH2. In the left side also we have CH2. But this molecule is symmetrical in nature or not? At the both position we are having CH2. Already we know that at least we need one hydrogen at the adjacent carbon. So here we have one hydrogen, here we have one hydrogen. So we will apply the reaction on both the sides. So CH2OH, CH2OH. Simply here hydrogen is replaced with OH, here hydrogen is replaced with OH. Similarly, see this nitrogen oxide, nitrogen and oxide. Okay, it is CH3, it is CH3. So CH2OH, CH2OH. This OTBDSP is tertiary butyl diphenyl silyl ether. We can represent in this way. Okay. So in case of the last example, if you see, we have two pyridine type rings, but one is the pyridine, second one is the pyridine N oxide. This reaction is only applicable to pyridine N oxide. That's why this portion will not be involved in the equation. So here we have acetic anhydride and reflux. There is no hydrolysis phenomena. See this one N oxide, we have CH3 here. If you do the hydrolysis, it will come up with CH2OH. But here there is no hydrolysis, up to the reflux only. That's why we need to come up with CH2OAC, CH2OC double bond O, CH. If you do the further hydrolysis, if you have the flexibility for the hydrolysis phenomena, then only we will come up with this type of compound. Methyl nitrogen CH2OH. Since here hydrolysis phenomena is not there, that's why there is no chance for the formation of this moiety. The reaction will be ending with this moiety only. So in this way, we can convert 2-methylpyridine N oxide derivatives into the corresponding 2-hydroxymethylpyridine derivatives by using Boekelheide reaction. Thank you very much.